So welcome back. Hope everyone's freshly caffeinated to pay attention to this next wonderful talk by Eusebio Gardella, who will talk about isomorphisms of Banach crossed products.
Yeah, thank you, Karen, for the introduction, and I want to thank the organizers for the invitation, also for organizing this nice event. Right, so this is the title of my talk. This is joint work with Tadeo Roland, who is a master's student now in Uruguay, who just started his PhD. And I want to start the talk by with a motivating theorem that is by now actually quite old, so it's from the 50s. It's a theorem of Wendell. Surprisingly unknown, but with a beautiful statement. So it says the following: let G and H be locally compact, okay, always including Hausdorff, groups. The most common thing to do in harmonic analysis, or at least abstract harmonic analysis, when you have a topological group, is to look at the L1 algebra, L1 Banach algebra. And you usually regard it as a Banach algebra with a convolution product, not just as a Banach space. And the theorem of Wendell says that there is an isometric isomorphism between two of these L1 or the convolution algebras. I emphasize isometrically. And I also emphasize as Banach algebras. Precisely if there is an isomorphism between G and H. So these L1 algebras actually have all information about the group, the algebraic structure, but also the topological structure. Right, and I think for my talk one can take this as the kind of the starting point. We are interested in finding analogs of this result for dynamical systems. So instead of just having a group, we want to have a group action. So G will act on a compact Hausdorff space, H as well. And we want to explore analogs of this result in this context.
Sorry, just a question. I mean, if it's not isometric, I mean, if it's just a Banach isomorphism, is it?
If it is contractive, you can still get away with it, I think.
What kind of hard measure is involved in this statement?
It doesn't. I mean, yeah. The unique up to scaling.
Scales.
Yeah, but then L1 will be the same. Isometric will be the same.
Strong theorem.
No. I mean, this doesn't depend on the choice of the hard measure actually. It's the isometric isomorphic if you change the scale. And if it is a contractive isomorphism, you can still get the theorem. But as soon as it's not contractive anymore, then you cannot get it anymore. I think there's some examples are easy. So Z4 and Z2 cross Z2. So they are, they have the same dimension as, and then there's also a constant very close to 1, so that if you have an isomorphism with norm at most that constant, then the result still holds. So it's like 1.0 something, I don't know. I think, okay, I don't know much more about this, but it is very important that here you don't allow norm increasing maps. Perhaps also worth mentioning is the fact that these algebras are also star algebras. So there's an involution in L1. For the theorem, you don't have to assume that the isomorphism preserves a star. In retrospect, if there is any isometric isomorphism between them, there will also be one that preserves a star. I mean, from this you get that. But you don't have to assume this to begin with. Right. I find this theorem absolutely fascinating, and if you have never seen it, I think it's can think for the whole hour about that. Probably it's more interesting than things I will say. But in any case, I want to go to dynamical systems, and I should also mention that although this theorem, as I stated, and also its proof is of course for all locally compact groups, the proof becomes easier when the groups are discrete, but also the main ideas are already there. So it's not that you're really significantly simplifying the situation. And today, from now on, I'm going to talk about only discrete groups. Make some of the arguments a bit more transparent, but the key ideas are always are all present there. So from now on, discrete groups, and I will not say this anymore to save time. And I will define the objects of study. Let me maybe even start by saying what. So actions for me will be always by homomorphisms. So an action of G on a compact space X. Compact for me always includes Hausdorff, at least for this talk. So the action will be written like this. So this will always be via homomorphisms, so no partial actions. And later we will consider X with discrete topology. So this is just to clarify that X has a topology to begin with, and we always act by homomorphisms. And the algebra we will study, the analog of L1 of G, is this one, little L1, because the group is discrete, of G acting on X. This is the notation that I would use. So to be the Banach algebra so that has every Banach algebra has an underlying Banach space. The underlying Banach space here is L1 of G, comma C of X. So I told you already what the norm is, what addition is, what scalar multiplication is, and I have to tell you what the algebra multiplication is. Okay, multiplication.
Sorry.
Yes.
The definition of l1 C of X, the separability of X is no role.
Separability?
Of X, yes.
I don't think it's. I mean, L1 of G, comma any Banach space can be defined. It's just you can, for example, consider finitely supported functions from G into that space with the L1 norm. So the sum of the norms, norm applied here, so it's infinity norm, and then completing that.
Yeah. X.
Yeah, exactly. So the multiplication, I will tell you, the elements here are generated by sums of elementary functions, some functions that are supported on just one element. The group is discrete. So it is enough to tell you how to multiply f delta s with g delta t. And by this, so f and g will be functions in C of x, and s and t will be elements in g. And this, of course, determines the multiplicative structure after you check that this product is contractive, bicontractive. In any case, this is like that. F, S acting on G, delta ST. So here's some quantifiers for Fg and C of X, ST and G, and this S acting on G is another function in C of X, which at the point lowercase x is G of S inverse X, and now this dot is according to this action. Okay, so this defines a Banach algebra, and just to be very explicit, the norm of an element here is this, you add, as you would in any L1 norm, the infinity norms of the evaluations of the elements of G. Okay, so I'm not sure how many times you've seen this algebra. This gets perhaps not exactly this one necessarily, but before you take completion, if you just take the compactly supported, in this case, the finitely supported functions from G to C of X with exactly this product structure and exactly this norm, this is the normed algebra that most often gets used in order to define cross products of C-star algebras, or C-star algebraic cross products. So let me remark this, that before I make this remark, there's also an adjoint operation in L1 of G acting on X, just like there is an adjoint operation here, that I'm not going to use explicitly just for this remark, but I think you can imagine what it is. So if you take the adjoint of this, you want to take the inverse of that, the conjugate of that, and flip them, and also bring them back. So by considering star representations of this algebra on Hilbert spaces, one constructs the full cross product C of X cross G. Very explicitly, what I'm saying with this is you can look at the family of all representations of this algebra on Hilbert spaces, preserving the star, and define a new norm as a supremum of the norms induced by these representations. And the completion of L1 of G acting on X with respect to this norm is by definition.
So one remark, you could just consider just contractive homomorphism. You will get the same.
That is right. Okay,
that's
that's right. Maybe that's more transparent. Thank you. Yeah, exactly. Thank you. That's right. Yeah. Right. And I'm assuming that all or almost all of you are familiar with C-star algebraic cross products. I'm definitely not going to assume that you are familiar with LP cross products, but I want to tell you, I will need them, so I'll have to say a few words about them. So before I go into that, I'll make an explicit remark of how do you get the reduced C-star cross product. You probably know that this is the completion of this algebra in one specific representation. So I think the way that I'm going to present it now is, I've never seen it before. I read your paper, Bartosz. So I think this is Bardadin, Kwasniewski. It's in the N. Yes. Very good. Very good, but not really. Okay. I will define a one very concrete representation of my algebra L1 of GCX, L1 of G acting on X, on one very specific Hilbert space. So it'll be, so it's L2 of just a product space, G cross X. And notice that when I do this, I kind of ignore the topology on X and I just look at it as a discrete space. So I give it the sample measure. So let's see if I can remember. So I will define this representation. It is enough to define it on generators. So this acts on this Hilbert space. So given a vector and a point here, Tx, what should it be? So it should be S inverse T, S inverse acting on X.
F should be somewhere.
And
F of.
oh yeah, F should go here. Yeah, times F of Tx. Sorry about that. So F multiplies.
It should be F at a point, I guess.
Yes. The action should be involved.
F. Okay, now I get confused. F of t and at x.
TX, I would guess.
Yeah. Oh, so I think it should be f of x. Sorry, so because I'm thinking that f is already.
T acting on X or something.
Yeah. F is already a function in CFX. Yeah, sorry, I'm confusing the two pictures. Okay, so this defines a representation modulo. Some mistakes I might have made, but I think the formula is correct.
I think it's easier to use like convolution formulas rather than action on the basis.
Yeah. Okay, now it's too late. So this defines a representation of L1 on a Hilbert space, and the completion of the closure of the image of this representation is the reduced cross product, C-star cross product, that I'm assuming everyone is familiar with. There's a somewhat recent field or like direction of study where people have studied operator algebras on LP spaces. The principle is very similar. You regard C-star algebras as acting on Hilbert spaces, and these are L2 spaces, and now you want to replace L2 spaces with LP spaces. And if you have a dynamical system, so G acting on X, you can also take its LP cross product, and at least formally in the definition it looks very similar. If in this you replace L2 with LP, you also get a contractor representation on that Banach space, and you can define the completion to also be, or you can define the completion to be the reduced LP operator cross product. So also remark, one constructs full and reduced LP operator cross products and since I will perhaps need a notation, I will just write it like this. So this is the full one, and the reduced one, I'll write it like this. Similarly. In particular, you have one for p equals 1 that I want to warn. It's not the same algebra, actually. So this L1 of G acting on X so this warning is only a warning for people that know these objects, and probably I'm not talking to too many of you in this moment, but L1 of G acting on X is not isomorphic to any of these, at least not in an obvious way. Very specifically, I'm saying that even for p equals 1, that representation that you get when you replace this 2 by a 1, it is contractive, it is injective, but it's not isometric. And in fact, this algebra L1 of G acting on X, as far as I can tell, is not really an operator algebra. So you cannot represent it as isometrically as operators on a Banach space in a useful way. Okay, it acts on itself by multiplication, it's unital. And so every unital Banach algebra acts on itself isometrically. But that, if you want to study this as a Banach space, it's not a very friendly Banach space. So I don't see any obvious way of studying this algebra as an operator algebra. And this actually will be useful later, or will be important later. I'm not sure if useful is the right word, but it will definitely be important. Perhaps another word of warning, if you think, okay, this is probably like doing C-star algebras and you just have to worry about the, slightly different norm, but things, this norm, although it's very explicit and all the elements of the algebra can be explicitly described, the norm is not very friendly. For example, problem is not really the word, but one difficulty is this one. let's say that G acts on X and G acts on Y, so G acts on two different spaces. And now you look at the action on the disjoint union. Your intuition from operator algebras would tell you that this should be isometrically isomorphic to the direct sum of these two Banach algebras. Okay, there's a slight question about like what norm you put here. I think perhaps the most natural thing to think about is the sup norm. For that one, it is not isometrically isomorphic, and actually, maybe there is a norm that you can define on the product of abstract Banach spaces, so that in this case you get an isometric isomorphism. I couldn't figure out what that norm could be. It's actually not very. It is really unclear.
L1 sum is
No, also no. The thing is that in this object, you're mixing L1 norm here and supremum norm here. It looks a little bit. It's also not like this, like the I norm in a groupoid. You know, when you have one thing on the base and another thing on the. But it's also not exactly that. So. Okay, so this is unclear, and then this is just one little taste of what difficulties in dealing with these.
So this is just because the action mixes the sets, right?
No, it doesn't.
It's no. The action doesn't. Yeah. So it's like you act here, separate. I mean, the topologies are also completely independent, you know, and then you still cannot, in a concise and natural way, describe this algebra by looking at these two parts. Right. Okay. So let me leave that aside for now. Maybe. Just the only remark that I will use from all of this discussion is that there is a contractive injective representation lambda sub 1 that looks exactly like that, but acts on L1 of G cross X. And this is something I will need later. So there is a contractive injective representation. It's not in general isometric, but that's going to be helpful to us. Okay, so I think now I can pose a question. What can you say about G acting on X and H acting on Y if these algebras are isometrically isomorphic? And isomorphisms for me are always isometric. Yeah, I don't want to spoil the answer yet. The answer will come at the end. So the first thing, of course, you want to relate the dynamics in a certain way. So the first thing that I will say without much explanation is that the copy of C of X inside of this L1 algebra can be detected. So let me write it like this. And by the way, when I say the copy of C of X in there is just supported on the unit of G. So the functions that look like just F times delta 1. So that's an isometric copy of C of X. C of X is the largest C star subalgebra of L1 of G acting on X. And I'm not saying that it's a maximal C star subalgebra, I'm saying that it's the largest. There's nothing larger than that. And it's also, the unique, unique largest, in any case.
But this seems to refer to the involution.
Good question. Yes, it does. it seems to refer to the involution, but there's a way of characterizing C-star algebras among Banach algebras without using the involution, actually. And just very briefly, I'm not going to write anything down, so it has to do with Hermitian elements. So Hermitian, the notion of a Hermitian element is an adjoint-free version of what a self-adjoint element would be. You just look at spectrum in a careful way. And Banach algebras that have sufficiently many Hermitian elements are precisely the C-star algebras. And then, how do you get the star? Well, the Hermitian elements, they're supposed to linearly generate the C-star algebra, and you're going to find a star like this. On the Hermitian elements, it's nothing, but on I times Hermitian elements, it flips the sign. So it's minus I times that Hermitian element. So there's a way of making sense of this without explicitly using the star, and this is what we do.
Is this largest in the sense it contains every other one?
Exactly. Any other C-star subalgebra will be contained in there. Exactly. Yeah. So of course, any isomorphism of these algebras will map one into the other. So automatically from this.
So is it important that you are considering commutative C-star algebras?
Yes. Yes. Yes, yes. I wouldn't know how to. I'm sure that there's something that can be done more generally, but we're definitely using the fact that, I mean, alone for the fact that I want to represent things on L1 of the same space. You know, this L1. So I want to put the same space here. So even if you put a C-star algebra, I don't know what to do with. I mean. It's unclear. It's a bit unclear what to do. Maybe something can be done, but it's unclear. In any case, we deduce that C of x can be recovered from this algebra. This is already very good, but we want to recover also something about the dynamics. How do we do that? And for that, I need, just like I needed an adjoint-free version of what a self-adjoint element is for Hermitian elements in order to get this. We will need to consider an adjoint-free version of what a unitary is, what a unitary in a C-star algebra is. The correct term is probably invertible isometry because that's really what they are. For this talk, I would just call them unitaries, although it's slightly confusing, but I think it makes some of the statements easier. So if A is a unital C-star Banach algebra, an element UNA is said to be a unitary, but really invertible isometry is the correct term. If U is invertible and both it and its inverse have norm 1. Okay, the term is not, does not create a conflict with C-star algebras or with B of H, because an operator in B of H that is invertible and that has norm 1 and its inverse has norm 1, also it's necessarily a unitary, so it's F non-DF. So remark, if A is a C-star algebra, this is the usual notion. And people that work in C-star algebras are used to know, to use in the fact that there's, in general, many unitaries in a C-star algebra. In fact, every element in a C-star algebra is a linear combination of 4 unitaries. On the other hand, in Banach algebras, there could in general be very, very, very few unitaries. And this is a source of rigidity. Of course, any automorphism of your Banach algebra, if it's isometric, it will preserve the unitaries. And in a C-star algebra, this comes with a lot of flexibility because there's so many, so a unitary will map to any of the other many unitaries that you have. But in a unital Banach algebra with very few unitaries, you have very few options of where to send your unitaries. And this ultimately will imply that there are not so many isometric isomorphisms. And this is kind of what is behind many of the things that I'll talk about. So the lack of unitaries is a source of rigidity. How am I doing with time? So I will ultimately need to compute the unitary group of the algebra that we're looking at. By the way, this curly U, borrowed from C-star algebra notation, stands for the unitary group. And for this, I will need a theorem, also a famous theorem, a very old theorem of Lamperti. And I will just state it in the context that I need it. So it's maybe, since we're in the Banach Center, I should call it Banach-Lamperti. So Banach proved it for the unit interval, and Lamperti did it for general sigma finite.
Just stated it without a proof.
But okay,
Banach just stated it.
That's true. I don't want to say that he didn't have a proof. In any case,
He found it. He found the theory.
found it under a stone, yes. But so it says like this. So let y be a set with a counting measure, and I would use it for p equals 1, but just to show you what it does in general. So you can take any exponent which is not 2. So you're excluding Hilbert spaces explicitly. And now you take a linear map from LP of y to LP of y, and you wonder when is that a unitary. And there's actually there's very few. There's a very rigid form, a very explicit formula for it. If so, I will just write the formula first and tell you what the symbols mean. So u of psi at y. So how can you get a unitary, an invertible isometry? You can first of all multiply by a function of modulus 1. This, once you compute the LP norm, multiplying by a scalar, modulus 1 doesn't change anything. And the other thing you can do is permute the elements of y in sigma, where f from y to t is a function. I mean, measurable doesn't make sense because y is given the trivial sigma algebra. So this is a function, and sigma from y to y is a permutation. So
One more historical remark.
Yeah.
For small LPs, Banach actually gave a proof. So this is Banach here.
Even better. That's really good. But by the way, if anyone ever teaches measure theory, the proof of this statement is actually super accessible. You could give it as a homework exercise, or I mean guided probably. But it doesn't use anything deep. It's just really actually basic computations in the complex numbers. It's really nothing, or convexity of functions. And there's nothing seriously deep going on here. Not to discredit Banach, but I mean, you know what I'm trying to say. So as an example, what it's actually gave to you, to show you how strong this result is, let's look at just M2 identified with B of LP of 2 points. And when I say identified, I mean algebraically, but very particularly I mean with a norm. Yeah. So what are the unitaries? So of course there's an answer for every P, and there's actually 2 possible answers. If P equals 2, the one that is excluded from this, you know that a matrix is a unitary if and only if its adjoint is the inverse, right? So U is a unitary if U star is the inverse. Yeah, now the star is, okay, we explicitly define transpose and conjugate. If P is different from 2, U is a unitary if U has either this form or this form, where lambda 1 and lambda 2 are complex numbers of modulus 1. There's actually very few. Of course, all of these ones are examples of those, but we all know that there's many more matrices satisfying this condition than those. Yeah. So again, this is showing that outside of C-star algebras, which by the way, when P equals 2, this is a C-star algebra, outside of C-star algebras, there's in general very, very few unitaries. So what's next? Right, again, our goal is to compute the unitary group of our L1 algebra and proceed from there. When X is totally disconnected, there's something that can be done for the L1 operator cross products. Since it looks really, since I think the statement is very pretty and it connects with some of the talks yesterday with topological full groups, I will state it. So this was a result with Matthias Palmström and Hans Thiel. Suppose X is totally disconnected. Then there is a short exact sequence. So in the middle you have the group that you care about, which is, well, almost the one that you care about. I'm using here L1 operator cross products, which is the completion of the algebra that we're looking at in the representation into L1 that I described. And there's a normal subgroup given by the functions from X to the circle, the continuous functions there. And the quotient is, I don't have enough space, the topological full group. Not just that, this is actually the connected component of the unit. This uses the fact that X is totally disconnected, and thus the topological full group of the action, which is the same as the topological full group of the transformation groupoid, if that's the way that one thinks about it, can be recovered from this algebra, which is not quite the one that we're interested in, but very closely related, as path components of unitaries. So U sub 0 stands for the connecting component of the unit. In the norm, I'm using the norm. So one can intrinsically, from this algebra, recover the topological full group of the action. This is actually already kind of good news for us. It's not quite the algebra we're looking at. And I will tell you, what can be done. So we cannot really use this, but what we can do, we can look at lambda 1, the contractive and injective representation of our L1 GC of X algebra, essentially into this. It will map unitaries to unitaries. Yeah. So in the case that X is totally disconnected, we can use this description because any unitary in our algebra will map to one of these, and perhaps you can try to see which ones actually are in the image. If the space is not totally disconnected, this is a bit more tricky. But I can tell you what we get. Gamma 1 of the unitaries is contained in something that looks at, I mean, it's a bit larger than this, but I'll just write it. Things that look like sums, index over the group of f times an indicator function of a subset x sub s and a group element lambda s, where f is just some function, but not continuous or measurable or nothing, because as before, you know, we in this representation we look at x with a discrete topology, so this is just a function, and the x's may partition x, but again, I'm also not claiming that they're closed or open or nothing. This is just a partition. Yes?
I think Jean Renaud or Hiroki Matsui had a similar kind of sequence for cross products. Can you comment on
Yes.
which one, how they're related?
Yeah, so it looks, I think this looks essentially the same in their context. Maybe they need to assume that it's essentially
They
relatively free or something. I'm trying to think whether they need effectiveness or not. It looks very similar. So what is crucially different in this context compared to theirs is that this subalgebra is intrinsic. So in C-star algebras, the copy of C of x in a cross product is not unique in any way. It could be anywhere. In our context, it is intrinsic. So for example, this cannot, I mean, this is not true in C-star algebras, just because you cannot identify this with the connected component of the unit. So yeah, it looks similar, but there's some advantages in this context. I mean, for the algebras that I am looking at, it looks even more different.
Could you say again what is capital lambda 1?
This lambda 1. So I think 2 boards ago here there was a representation lambda into L2, and when you replace a 2 with a 1, that's lambda 1. The formula is exactly the same. Yeah. And right, so what happens? So this, I'm not skipping anything, so this is actually what one can get with some work. One doesn't know much about this partition, and one also doesn't, in principle, a priori, doesn't know much about this function f. But this representation lambda 1 is so canonical, in particular injective, that using this one can improve the result, the description.
This still assumes totally disconnect?
No. I'm forgetting the topology actually right away when I take this representation. Let me try to get to that. Sorry, okay, I should be able to remember what I'm trying to say. So this is the result with Tabaré. It's kind of where the key is. There is, for any dynamical system, so now I'm not assuming anymore that X is totally disconnected, but instead I'm looking at the other algebra that I like, L1. There is a short exact sequence. It will look very similar. A normal subgroup is continuous functions into the circle. Now again, this is the unitary group that you're interested in. And what is the quotient? The quotient is G. And I want to say perhaps 1 or 2 words about why you get G and not something like a topological full group. In the end, what you want to discard is a situation of the following kind. You have a unitary here, first of all. You map it to the l1-crossed product. And let's say that it's a proper topological full group element. So it's a sum of 2, let's say, so f times x1, so f1 x lambda s1 plus F2 something like this. And let's say that we're in the best of the worlds. X1 and X2 are clopen. So this is it really looks like an element of the topological full group when you think of this. And then these are continuous functions into the circle and so on. Why would an element of this form not be a unitary in my algebra here? And this is like the one place where you're actually happy about the norm on L1 of G acting on X, because this is just an L1 norm. The norm of such an element is the norm of this plus the norm of that. And the norm of this is actually 1 as soon as X1 is not empty, and the norm of that is also 1 as soon as X2 is not empty. So this doesn't have norm 1 unless you have exactly one summand. And when you have one summand, this just corresponds to one group element. And this looks like I only did it for 2 summands, but if you have more, it's even worse. Yeah. So this is how, very roughly speaking, one has to do a lot of work, because in principle this function doesn't have to be even measurable. It's just and this partition is in principle very ugly. One can prove that if it comes from an element here, then the function has to be continuous, the partition cannot be too bad, and ultimately what it boils down to is an argument of this form. If you have a proper element of the topological full group with a proper partition, the norm is bigger than 1, the L1 norm is bigger than 1. So what we get from this is that not only C of X can be detected in L1 of G acting on X, but also G can be detected. Perhaps I should say how it is detected. This is not in general the connected component of the unit here. If the space is, if X was connected, for example, you have no hope of. But the copy of C of X, and therefore C of X, comma T, this is intrinsic to the algebra. So since this is of course intrinsic, and this is intrinsic, well, and their quotient is also. So, and this is perhaps at first sight a little bit surprising. Well, I don't know, to me it was surprising, because I was always expecting that this algebra would be more closely related with the transformation groupoid, G cross X, than the actual action. But of course the transformation groupoid doesn't know who the acting group is. It does know who C of X is, so until here, and it knows who the topological full group is, so until here everything would have indicated that this object actually only depends on the transformation groupoid, but once you get here and the group can be recovered, then it's a bit finer than that. One remark is that this already implies, so everything that has been done until now already implies Wendel's theorem, at least in the discrete case, because if you forget, if you take X to be a point, then this is really the L1 algebra. This implies Wendel, at least in the discrete case. And actually, if you specialize to the case that Wendel studied, the proof is also different. So this is, even in this setting, it's not the same proof. But we want more. So we know we have the group, we have the space. Of course, now we want to know where the action is. How do you get the action? And now this is not too hard. So what happens is that so the unitaries of your algebra, well, they act by conjugation on the algebra itself. Yeah. So U inverse. Now, okay, it's unfortunately erased, but what I wrote here was that C of X is the largest C star subalgebra, and therefore it is preserved by isometric isomorphisms. Conjugating by unitaries gives an isometric isomorphism. And therefore, so the action that of course you have on G acting on X restricts to the largest C-star subalgebra. So you get an action of the unitary group on C of x. So again, this is very specific to this context, and it is because C of x is a unique subalgebra here with a certain property, and a property that is preserved by isometric isomorphisms. So what happens is that when you look at the short exact sequence written over there, I mean, this action is by conjugation. C of x is commutative. So all the elements here will act trivially, just because they commute with anything in C of x. This action is trivial on the unitaries of C of x, which are the functions from x to t, and therefore gives you an action of the quotient well, an action on C of x, but it's the same as an action on x. Yeah, it's not a coincidence. This can be identified with the action that you started from. And for this, I need definition. Two actions. I wanna say that a priori, the action that you start from, G on x, and this one, okay, there are two actions of G on x, and they are the same, but one has to, of course, also do that. It's not a difficult argument, but yeah. So two actions, G acting on x, and H acting on y, are said to be. I don't know if the term is standard, probably not, and I'm not sure that it's the best one. I will call them weakly conjugate. I definitely think that conjugate is not a good term for this. If there exists an isomorphism of groups, and a homomorphism of spaces such that, so when you have G acting on x and you apply theta, this is the same as phi applied to G acting on theta of x. In some sense, it's the most natural notion of isomorphism for actions on spaces, actually. And the reason why I don't want to call this conjugate is that when you have a single transformation, so an action of z, you would be saying that the action and the inverse are also conjugate, but one calls that flip conjugates. So I don't know. If you have a better name for this.
Isomorphism of dynamical systems.
Yeah, maybe, yeah. Isomorphism is overused, but okay, I think it's better now. Yeah, thank you. Good. And then the actual statement, and I avoided saying it for a reason, is that this action is isomorphic to the original one, but it could be that you have to permute the group elements. It could be that you have a group isomorphism there. So now, I'm ready to state the theorem. There is an isometric isomorphism between L1 of G acting on X and L1 of H acting on Y, if and only if there's an isomorphism of the actions. And this, yeah, again, when we started looking at these things, I was expecting that the outcome would have to be with orbit equivalence or continuous orbit equivalence, because I was expecting that it's actually transformation groupoids that are the ones who have more things to say, but it turns out not. It turns out that L1 of G, X, or acting on X, is a lot more sensitive And yeah, maybe just to close, I mean, in my eyes at least, this opens the door for exploring questions of the following sort. You know, this algebra with its norm knows everything about the dynamical system except possibly what is future and what is past. Yeah, so future orbits and past orbits, if it's a z action, will mix. So this you have no hope to be able to recover. But everything that depends only on the isomorphism class of the dynamical system will be encoded there. And now, but how exactly is it encoded? And what is particularly interesting is try to read off of this algebra topological dynamical properties of the dynamical system that cannot be read off of the C-star algebra. This I think will be super interesting. You can read off of it some properties that in C-star algebras we're also used to be able to read, so minimality, topological freeness, also with similar characterizations actually, this ideal intersection property and things like this. But for example, this theorem of Tabaré I find really interesting. I should say also this is a precursor due to the Joe and Tomiyama. So let G be torsion free and abelian. So for example, the integers z to the d, q, etc. Then G acting on X is free. So the action is free, which is something that you cannot detect with C-star algebras, if and only if every closed ideal in L1 is self-adjoint. And again, I find this really interesting because freeness is a property that you typically cannot detect in the C-star cross product. And the way that you characterize it is by something that is automatic in C-star algebras. So I think it would be super interesting to explore more things of this kind, detect topological dynamical properties of the system in similar ways, I mean not similar ways, but in a similar spirit. Yeah, so I think that's all my time. Thank you so much.
Eusebio, do you have any questions?
So what about if you consider just the multiplier algebras of L1 of Gx? You know they are isometrically isomorphic.
Right, so if you go back to the group case, this is Johnson's result. Okay, but these ones are unital when G is discrete and you look at little L1. So there's nothing, I mean, what you probably have to do if you want to extend this to, for example, flows or something like this, you definitely will have to look at the multiplier algebras, because I still think that going through unitaries is what you should do. Now it's much more subtle because you probably have to look at the strict topology. You have to be more careful, but you probably will have to look at the multiplier algebras of these things. It's a very good question for sure.
Yeah, I really like this result actually quite a bit, and I was curious. I don't know if you have any ideas or thoughts on that. If you could capture things like like if you have a free abelian group, can you capture the rank inside the algebra? Can you capture the entropy of the system or invariant measures? That could be probably related to characters or traces in some way.
Yeah, so invariant measures are. Yeah, absolutely. In principle, yes, because you know everything about the system, but how exactly you detect it, I don't know. Just like in principle, I mean, freeness is encoded, even without this assumption, but how exactly, I think the one that should be attacked first is the one with invariant measures, because it should be related to traces. But I don't know, actually, I never did anything.
Can you expect such a result also in the locally compact case, general case?
I think so, yeah. Yeah. I would, I mean, my guess would be yes. I really think so, yes.
There are some groups where you have a unique C-star norm on the group algebra. Right?
Yeah.
Anything additional if I look at actions?
I never looked at that. It's a good question. I don't know.
Okay, there's one more question.
Like, you expect something for thousand points? Equivalence relations?
Yes, I think so. I think, okay, let me... Okay, the first question is what algebra you look at. And one possible candidate is the I-norm completion of the CC functions. And I think...
But this is not exactly, this would not correspond to what we have here.
No, exactly. So even if you start with an action and you look at a transformation group and you do this, what I'm describing, it would not be the same algebra. But so it's just a result that goes in a similar direction, but it actually does not generalize it because it really depends only on the transformation groupoid, which is coarser than this. If you have a groupoid, let's say an ample groupoid, and you look at the I-norm completion of the CC functions house of groupoid, we proved with Hannes and Matthias Palstrom that the I-norm completion completely recovers a groupoid. And I think, I mean, without ampleness, I think we also know it by now, but I'm not entirely sure. But that's so I think for groupoids and I-norm completions, one can also do something like this. Yes.
So did you use this result? Because I kind of was confused. Now this with discrete, with total disconnected space. So was it used in this theorem?
No,
it was not.
It's not explicitly used because, of course, it assumes some things that we don't want to assume. I stated it because I thought with the topological full group, I mean, yesterday there were a lot of talks about topological full groups, and I thought it looked nice. But what the actual reason why I mentioned it is that the techniques, we kind of recycle some of the techniques. You know, without total disconnectedness, you cannot get so far, but you can get far enough that it is good enough to get a description of the unitaries.
Okay, so let's thank Eusebio again for. And we resume in 7 minutes.
Because you can easily, like in the C-star, and you can easily find equivalence